Hi everyone, I'm Sergio Casas and today I'll be presenting our work on incorporating prior knowledge for precise multimodal prediction. In a traditional self-driving pipeline, we receive information about the surroundings through sensors. Here we show a top-down view of a LiDAR point cloud as an example. We first localize the vehicle such that we can exploit high-definition maps. Then we perceive the current state of the world from maps and sensors, and subsequently perform long-term motion forecasting to predict the other actors' future trajectories, which are then fed to the motion planning as obstacles to plan a safe maneuver, and finally a controller calculates the necessary steering and acceleration. In this work, we focus on the task of prediction and how this affects motion planning. More precisely, we are interested in predicting a distribution over each actor's future trajectories y given an environment observation x. We would like a model that first captures the inherent multimodal uncertainty of the future. In the illustrated example, a vehicle may choose different paths and may execute different speed profiles. This is particularly challenging to learn because in observational data, we only observe one realization of the future, but there might be others that are equally valid. Second, map understanding is critical to succeed at this task. For instance, a good amount of behavior multimodality arises from branching map topologies, such as the one depicted in the example. Luckily, we can exploit our prior knowledge that vehicles tend to follow the lane and rarely drive off the main road, although we need to take into account that some drivers may be non-compliant. Lastly, actors interact with each other and generally exhibit socially consistent behaviors. In particular, we want to accurately predict actors that may interact with the self-driving vehicle. In order to plan a safe maneuver in complex traffic, the motion planner takes into account the other actors' trajectory distributions as obstacles. Therefore, for the motion planning to see a faithful representation of how the scene might unroll, it is important to achieve a high precision and recall. This means that we want to cover the ground truth distribution without generating unrealistic samples. To illustrate this concept, on the left we have an accurate model where the ground truth distribution in black and the predicted one in purple nicely overlap. On the middle, the predictions recall or cover all the two trajectories, but we also observe unrealistic samples, which we refer as low precision. On the right, we have the opposite case, where the model achieves high precision but low recall since it doesn't cover all modes. Many probabilistic formulations have been proposed to capture multimodal uncertainty, with different pros and cons in terms of expressivity as well as computation and memory complexity. Some examples are mixture of Gaussian trajectories, where a small number of modes are considered and for each mode is composed by a sequence of varied Gaussian waypoints. Occupancy grid maps, where a classification is performed over a bird's eye view grid for each future horizon. The problem of motion forecasting can also be reframed as a multi-class classification over a predefined set of trajectories. And finally, autoregressive approaches where the one-step conditional distribution is modeled instead of the trajectory marginals have also been proposed. In this work, we perform our experiments with a mixture of Gaussian trajectories, although the rest of the parameterizations will also fit our framework. The methods we've just covered are typically trained with simplistic losses such as negative log likelihood or L2 error, which do not reflect well what truly matters for driving. Let me illustrate this with an example when using L2 error. The green trajectories represent the ground truth future behavior for the blue vehicle, and the red and blue trajectories are two predictions that have the same L2 error, yet very different impact in planning. In the left figure, if we predict the red trajectory, it will cause the SDV to swerve out of the road to avoid collision. In contrast, predicting the blue trajectory wouldn't have any impact on autonomy. A similar story holds in the right image, where if the red trajectory is predicted, the self-driving car would think there is no obstacle in front and could accelerate and get too close to the blue vehicle, causing a future hard brake. Something the previously proposed likelihood-based or L2 losses do not capture is how much drivers rely on the traffic lanes and rules. For instance, in the example below, we know it's more likely the vehicle continues straight or turn left than changing lanes crossing a double solid divider. Another aspect that we can incorporate is that there are some actors in our surroundings that are very relevant for our decision making because they can easily interfere with our future trajectory, and others that are not so relevant, for instance, because they are behind us. In contrast to previous works that incorporate inductive biases into the model, such as map relative output parameterizations, we propose to incorporate these priors in the form of additional loss functions. This has the advantage of being applicable to any probabilistic model of future trajectories and to still allow for flexible predictions of non-compliant behavior, as we will see later. However, this prior knowledge is generally hard to express in terms of smooth and differentiable functions. On the other hand, we can simply define them as arbitrary reward functions that are non-differentiable. The first prior we are interested in incorporating is the fact that vehicles tend to follow their reachable lanes defined by the map topology and traffic rules. To obtain these reachable lanes from our maps, we can associate each vehicle to a lane and query its neighboring and successor lanes, shown as the green shaded area. Then, we can reward predictions that stay within such an area and penalize the ones going outside of it, like the red trajectory in the left diagram. There is an exception though. Some actors behave in a non-compliant manner, such as the example in the right drawing. Because we want our model to still capture this behavior, we do not apply the prior loss when the ground truth doesn't follow the reachable lanes. This also makes our reward function robust to failures in the map. Finally, we can similarly reward high precision and recall of vehicles driving closely to the self-driving vehicle route, as these have more chances of interaction. For this reward function, we simply distinguish trajectory predictions that get inside the route versus outside of it. As you can see, our reward functions are not smooth on the trajectory space, and thus we need a framework that allows us to incorporate this non-differentiable prior knowledge. Let's get into the details. In our framework to incorporate prior knowledge, we assume we have access to the conditional distribution of an actor's future trajectories y given the context x. We can then write down the negative expected reward under the trajectory distribution and use this as a supervision loss, called L prior here. We can compute the gradients of this loss with respect to the parameters by leveraging the policy gradient theorem, which only requires us to calculate the gradients of the log likelihood, but not our non-differentiable reward function. Intuitively, the gradients will follow the direction to maximize the likelihood of highly rewarded trajectories and minimize the likelihood of less rewarded ones. However, integrating over the continuous distribution over trajectories is intractable, and therefore we approximate the expectation with Monte Carlo sampling. To obtain motion forecasts from sensor data in real time, we opt for a state-of-the-art joint perception and prediction model that shares features between both tasks, also easing the uncertainty propagation between them. In particular, we enhance the state-of-the-art perception and prediction model SPAT-GNN by replacing its unimodal prediction header with a mixture of Gaussian trajectories. For this, we leverage 3D point clouds coming from LiDAR as well as high-definition maps as input. In this framework, we first voxelize a sequence of LiDAR point clouds corresponding to the previous 1 second history into a bird's eye view voxel grid and raster the high-definition maps into multiple semantic binary channels. Then, we use CNNs to extract features from LiDAR and maps separately and fuse them by concatenating their channels followed by another CNN. Once we have rich features from the whole scene, we can obtain object detection, shown in red. Let's focus on one of the vehicles for now. Since we know the information ahead and to the size is the most relevant, we attribute this region of interest to the actor. Then, we can pull the features on that region as a summary of the actor characteristics. We can do this process for all vehicles in parallel. We can now further process the features with a CNN with global pooling and obtain a feature vector for each actor, which is passed to the prediction model. We use a spatially aware graph neural network as our prediction model, which performs message passing at the feature level across the detected actors to model their interactions. Finally, a multi-layer perceptron predicts the parameters of a mixture of Gaussian trajectories for each actor independently. This perception and prediction model is fully differentiable and can be trained end-to-end through backpropagation using a multitask objective. For object detection, a cross-entropy loss is applied to the detection scores, a smoother one to the bounding box regression targets. For prediction, a surrogate loss is used for improved stability during optimization. First, we define the true mode as the one which mean is the closest to the ground truth trajectory, shown in green, in this case the gray mode. Then, a cross-entropy loss is applied to the mixture coefficients and a Gaussian negative log likelihood only to the waypoints of the true mode. Despite its improved stability, this has the disadvantage that it doesn't give signal to the whole distribution. In this case, the orange Gaussian waypoints are left untrained. Under this multitask learning objective, we can easily incorporate our prior knowledge loss as an extra term. The only thing we need to do is sample many trajectories from the distribution, compute their likelihood, and apply the reinforced base gradients as explained before. A clear advantage shown by the prior loss gradients is that this loss supervises all modes through their samples, not just the closest one to the ground truth. Intuitively, this difference makes sense, since we can apply our prior knowledge loss to any sample because it's only dependent on the map and the self-driving vehicle route. In contrast, we only observe one future realization for likelihood-based training. To evaluate the map understanding, we can compute the final lane error. This is the percentage of samples which final waypoint disagrees with the ground truth in terms of falling inside or outside the reachable lanes. We do this for 50 predicted samples and only evaluate on moving objects since static ones are trivial. We also break down the results by high-level action. We can see our method shows gains over previous approaches. In particular, it is worth looking at Spagian N+, which is the exact same model as ours, with the only difference that it doesn't have the prior loss. Next, we evaluate the precision and recall of our samples. The mean average displacement error, or mean ADE, measures the expected displacement error across samples, being a proxy for precision. In contrast, the minimum ADE represents the recall of the ground truth realization by measuring the distance to the closest sample, as shown in the diagram. We can see our prior loss heavily improves the precision of our samples, although it trades off a bit of recall. As we will see in a couple slides, this trade-off will pay off. For now, I want you to keep in mind that minimum ADE is the commonly accepted metric for motion forecasting, despite the fact that it only measures a single sample, the best one. Here is a qualitative comparison of the same model without our prior knowledge loss on the top row and incorporating prior knowledge on the bottom row. The visualization blends in 50 trajectory samples for each vehicle. Transparency denotes its likelihood, and the color gradient the prediction horizon, as can be seen on the bar on the right. We can see that the baseline produces unrealistic samples going out of the map. In contrast, our model produces a realistic lane-following behavior for the same two cars. Let's look at an example where a vehicle is going off the road. We can see how our model can capture this behavior just as well as the baseline. We've been looking at direct evaluations of the motion forecast. However, despite having multiple metrics that attempt to evaluate different aspects of the distribution, there's always a disconnect between these metrics and the end goal of driving. To showcase this, we put our model in the broader context of the self-driving system to understand how it influences the safety and comfort of the self-driving vehicle plan trajectory. For these experiments, we use a state-of-the-art motion planner and pass in 50 trajectory samples for each actor from the prediction model to characterize the obstacles. We highlight that this sort of evaluation of the system-level impact has been overlooked by previous perception and prediction papers, despite its evident importance. We find that our model with prior loss, which had better precision but worse recall, enables much safer motion plans with a 17% drop in collisions from the strongest baseline, closer imitation of the human expert demonstrations, as shown by L2Human, as well as mild improvements on comfort metrics. These results show that motion planning performance doesn't necessarily correlate with minimum ADE, the most commonly accepted metric for motion forecasting, but rather with mean ADE, the average error across samples. We believe that after these results, the motion forecasting community should reconsider what to evaluate in benchmarks for this task and highly encourage them to include planning-centric metrics. Here is an example on why the precision matters for safety. The column corresponds to different time steps of the unrolled future horizon of 5 seconds. The baseline model without prior loss on the top row, ours on the bottom. We show the self-driving vehicle plan in blue, the expert demonstration in a black box without filling, the prediction samples are shown in yellow, and the ground truth trajectories of other actors in light gray, unless they are in collision with the SDV plan at any point, in which case we show them in red. Please focus on the vehicle of interest marked with a circle throughout the sequence. We can see how the predictions for the baseline get more and more fanned out over time, ultimately forcing this SDV to swerve into opposite traffic and collide. In contrast, when using our prior loss, both the predictions as well as the self-driving vehicle normally follow their lanes. In this video, we show 50 sample trajectories for each actor, blended with transparency and using the color gradient to encode time. We show the base model without prior loss at the top and ours at the bottom. The trajectory distributions become less entropic and follow the map better, which is clear as vehicles turn. As we mentioned earlier in the presentation, our method is able to capture non-compliant and off-road behaviors, as we can see in the video. Finally, here is another intersection that exhibits similar improvements as seen before. In conclusion, we have proposed a general and flexible framework to incorporate prior knowledge. Our approach works with any prediction model that provides a distribution over actor trajectories, doesn't assume the prior knowledge to be a differentiable function, and is able to capture non-compliant behavior as well, since it doesn't impose any hard constraint on the trajectories. We showed better precision and map understanding in the motion forecast, but most importantly that our predictions translate into safer and more comfortable motion plans. As future work, it will be interesting to see how our framework performs with different probabilistic output parameterizations, as well as to explore how to extend this framework to models that characterize the joint distribution over actors. Thank you.